Hi students, welcome to my lectures on chemical engineering thermodynamics. Before I start, I request you to follow my lectures from the beginning because every lecture is connected. In the today's lecture, what we are going to discuss about finding the properties in a mixture. Because in engineering, everything is a mixed state. That's why it's important to find out the properties of a mixture, whether it is gas mixture or a liquid solution. So you have to find out the properties of a mixture from the pure property data. That means if you know the example, in a mixture A plus B is there, I have to find out what is the property of A in this mixture and property of B in this mixture. And I have the information about the pure A and pure B and how I can connect the pure A and B with the A and B in the mixture. So this is what the relating the partial molar properties of the mixture with the pure molar properties of A and B. So how to connect the pure property and the mixture property? So here we Gibbs theorem, because using the Gibbs theorem we can connect these two. And what is this Gibbs theorem? Before I go into Gibbs theorem, I would like to explain that explanation of Gibbs theorem through this picture is very easy than compared to the reading the definition. What Gibbs theorem states? Gibbs theorem states that any partial property in the mixture can be known if you know the pure property of A. But temperature should be the same, but the mixture pressure is total pressure is P, then the pure property pressure should be partial pressure of A in this mixture. Let us go to the definition. The partial molar property of the species or components in this mixture, partial property of A and partial property of B, for example, at temperature T and pressure P of this mixture is equal to corresponding molar property of pure gas. Example, if A is in this mixture, then I know the value of A in this mixture if I know the pure value of A at that same temperature, but the pressure equal to the partial pressure of A. So equal to the corresponding molar property of the pure gas at a mixture temperature T, but at a pressure equal to the partial pressure of A. Symbolically we can represent. Any partial property is represented by M bar I. Any pure property is represented by Mi. The bar signifies I am talking about something in the mixed state. Without bar means it is in pure state. Then any property of A, example property of A in this mixture at a temperature T and pressure P will be equal to the pure property of A at temperature T but pressure at a partial pressure of A. Because every gas will have the partial pressure. The partial pressure of A, this is the partial pressure, the contribution, this is the fraction is Ya, the fraction is Yb. Okay. So this is what the Gibbs theorem states about MRI, Ig, because whatever things we are discussing is for the ideal gas, which obeys the ideal gas. Later on we will relax this assumption, we go for the real systems like non-ideal gas mixtures or non-ideal solutions. We can introduce the fugacity there, so it will be non-ideality will be again considered. Simple. Any property in a mixture which is following ideal gas conditions at certain temperature and pressure is equal to the pure property of ideal gas at temperature T but pressure equal to Pi. If I apply the Gibbs theorem for these conditions for the mixture, binary mixture of A and B, what is the partial property of A in this mixture at temperature T and P, which is equal to the molar property of A, pure property, at temperature T but pressure equal to the partial pressure of A. Similarly, the partial property of B in this mixture at temperature and certain temperature and pressure of the mixture will be equal to the pure property of B at temperature T but the pressure equal to the partial pressure of B. Okay. So this is how you can apply the Gibbs theorem. M, any property, it could be Gibbs, it could be Gibbs energy, it could be enthalpy, it could be internal energy, it could be Helmholtz energy, any property can be evaluated because using the Gibbs theorem. Let us apply the Gibbs theorem for knowing the enthalpy of A in the mixture and enthalpy of B in the mixture, provided you know the enthalpy of pure A and enthalpy of pure B. Let us apply the Gibbs theorem for the case of enthalpy. So imagine there is a mixture of A and B present at certain temperature T and P. The fraction of A is Ya, the fraction of B is Yb. I have to evaluate what is the partial enthalpy of A in this mixture and partial enthalpy of B in the mixture. And to know the partial properties, I should know the pure property of A. The pure property of A at same temperature but the pressure equal to partial pressure of A in the mixture. Similarly, if I wanted to find out the partial enthalpy of the B at temperature T and P, I should know the pure property of B at same temperature but a pressure equal to the partial pressure of B in the mixture. So H bar A and H bar B representing the partial properties, HA and HB is representing the pure properties. Okay, Ig means whatever the things we are discussing about the ideal gases. So partial enthalpy of A at T and P, which is equal to the pure enthalpy of A at temperature T and partial pressure Pa. Partial enthalpy of B at temperature T and P, which is equal to the pure enthalpy of B at temperature T, partial pressure Pb. If you remember ideal gases, okay, the gases which behaves ideally, the enthalpy depends only on the temperature, not on the pressure. So if I apply the ideal gas conditions for this Gibbs theorem, then partial enthalpy of A at T and P, which is equal to the pure enthalpy of A at T and Pa, which is equal to the pure enthalpy of A at T and P. You can replace the Pa with the P because enthalpy does not dependent on the pressure, only temperature should be the same in everywhere. Okay, similarly partial enthalpy of the B at T and P, which is equal to the molar enthalpy of the P at T and partial pressure B, which is equal to the molar enthalpy of B at T and P. So pressure does not matter, only temperature should be the same. That means if you know enthalpy of pure A at certain temperature, same is the enthalpy of A in the mixed conditions, provided the temperature is same for the both the cases. Okay, so let us apply this particular formula in one example. Okay, it will be more clear. Find example, there is a mixture which is at a temperature of 200 and pressure is 1 bar. That means if there is a component A and B in the mixture, I know the temperature and pressures. Okay, at 200 degrees centigrade 1 bar. You have to find out what is the partial enthalpy of A in this mixture, what is the partial enthalpy of the B in the mixture, and what is the total enthalpy of A plus B. Okay, so that is what this. Find partial enthalpy of A, partial enthalpy of B, and total enthalpy of A plus B in the mixture at temperature 200, pressure 1 bar. Okay, you have to find out. Given data, pure data is given. The data that is pure enthalpy of A at temperature 200 and 2 bar is given 30 joule per mole. Pure enthalpy of B is given at 200 and 2 bar 40 joule per mole. Fraction of A is 70%, fraction of B is 30% in the mixture. And if you observe, I have to find out the mixture property at 201 bar. But what is given here? The pure property values at 202 bar is given. Okay, then how I can know about this? Let us apply this particular formula to evaluate the properties of A and B in the mixture. According to this formula, enthalpy of A in the mixture at 201 bar will be equal to the pure enthalpy of A at 201 bar, which is equal to the pure enthalpy of A at 202 bar, because enthalpy of enthalpy of gas, ideal gas, does not dependent on temperatures as long as the data given at the same temperature, so you can take it as it is. So what is the pure partial, that is enthalpy of the A in this mixture, will be equal to the pure enthalpy at 202 bar, which is the same. So already is given 30, so you put 30. Similarly, partial enthalpy of the B in the mixture at 201 bar, which is equal to the pure enthalpy of B at 201 bar, which is again equal to the pure enthalpy of the B at 202 bar, because temperatures remain the same, so you can take value at 202 bar also. So the partial enthalpy of B is 40 joules. That means now you got the value of partial enthalpy of A, which is 30, and partial enthalpy of the B, which is again 40. Okay. Now find out the total property. Total property value is represented by Hij. Okay. If you summate enthalpy of A and enthalpy of B, then it will become the total property of the mixture. Then we use the summability relationship, which we have discussed in the earlier classes. Total property of the mixture, which is equal to sigma yi h bar I ig. So it is a binary mixture of A and B. If I expand the sigma, ya h bar A ig plus yb h bar b ig. I know h bar A ig, h bar b ig. I know ya is 0.7, yb is equal to 0.3. If I put in this formula, I got the number, the enthalpy of the mixture, which is A plus B, 33 joule per mole. Okay. This is how we have to apply the Gibbs theorem for the case of enthalpy. I hope you like the way of representation to understand the Gibbs theorem. And thank you. Let us meet with the, because we similarly we have to apply. That means you need to get the partial prop. Here you calculated enthalpy. Similarly, you have to get the value of partial entropy, partial Gibbs energy, because these partial properties are the helpful in finding the mixture properties, and then you apply for different applications in chemical engineering like separations, purifications and reaction. And thank you. Let us meet with the new lecture.